I think about solvation and hydration, I have a very specific mental picture about what's happening with the particles. So the goal today is to help you create the same type of picture. It may be something about the way the question was worded that prompted you all to think of a chemical reaction, or maybe because that was what we were talking about in the last chapter, so you're all already still in that mindset of a chemical reaction. But just to let you know, the word solvation, if you haven't looked at this yet in the chapter 9 that we're going to be covering today, solvation and the word dissolving, those two are pretty much reserved for situations that are physical in nature rather than chemical. So if you hear the term chemical reaction or chemical change, then you know something specific is happening. In a chemical or in a physical change, there may be something happening, but the difference between chemical and physical is that in a physical change, there's ultimately no difference in where the electrons, the valence electrons are and how they're arranged. So when you dissolve something, we are not changing how the valence electrons are arranged or distributed around these particles. So if I just give you some substances like KBr and water, and I say, what's going to happen? I don't really expect you to answer that, because that's a difficult question. Sometimes when I put certain things in water, I'll get a chemical change. Sometimes the initial arrangement of the electrons isn't very stable. And if I put something that's unstable in water and the electrons are not arranged in a stable way, well, then they will change their arrangement, and that will be a chemical change. So, for example, one of the types of reactions we talked about in the last chapter, if you were to synthetically create a neutral version of one of these group 1A or 2A metals like sodium, we don't find sodium like this naturally, right? It doesn't have a neutral charge naturally. In nature, it comes with a +1 charge. So if I force an electron onto that 3s subshell for sodium, and it has at 1/3 energy level valence electron, if that comes in contact with water, it will undergo a chemical change. Water, you would probably predict, is pretty stable. Right? Water accumulates in our environment in huge quantities because the oxygen and we have lots of oxygen and hydrogen on Earth, and that's a very stable way for them to arrange themselves with the right number of electrons to have no formal charge, complete their noble gas configurations. So water doesn't usually react with a lot of different things, right? If it did, it would be much less common naturally. But in this case, the water will react, not because it's unstable, but because the sodium is unstable. So what's likely to happen to the sodium? What? Right, it's going to react. So chemically, if it's going to react, that implies a change in the arrangement of the electrons. And so what we'd be looking for in a chemical reaction is, where are the unstable electrons? Is one atom pulling the electrons more than another? Are they going to shift from one atom to another? It's the sodium that has one valence electron that it doesn't need and can't attract strongly. Right? It has one electron in the 3rd energy level, shielded by all the electrons in the first 2 energy levels. That one valence electron of sodium can't get very close to its nucleus. plus that one valence electron, if it were lost, would leave sodium with the noble gas configuration, which should be way more stable. So what's going to happen is that electron is going to go over to the water. So if we imagine what the water looks like, where's it going to go? The water doesn't have any place to put it. The water already has a complete noble gas configuration. Can the water or the oxygen of the water just accept one more electron? No, it wouldn't be any more stable there than it would be on the sodium, because the oxygen has a completely filled second energy level, giving it a noble gas configuration. If it accepted one more electron, it would break that noble gas configuration. So that's what makes water so stable. So I'm not explaining this because I expect you to be able to recognize this. I just want you to understand the difference between a chemical reaction and a physical change in more detail. Now that we've talked about what makes molecules stable and how electrons need to be arranged to make something stable, you need to understand that if the arrangement of the electrons changes, that's a chemical change. And that will only occur if one of the two substances starts off with a relatively unstable arrangement of electrons. Then when the two molecules or two particles collide, there's a little energy, the electrons can rearrange their locations. In this particular example, if you're curious, what happens is this electron from the sodium will come in here, go to the oxygen, since it has a partial, since it has the ability to attract an electron better than the hydrogen, and then this bond will break. One electron will go to the oxygen and one will go to the hydrogen. And so then the oxygen will have a negative, and I will create a hydrogen temporarily with a broken octet. And then what does the sodium look like? Well, that would produce an Na+, right? Because now the sodium doesn't have that one valence electron anymore. So if I do that reaction again, because another sodium bumps into another water, I make more of these things, including another H radical. And then those two will join together to form a bond. So hydrogen gas is created. So that's the way I can eventually get all those electrons that were originally present arranged into complete noble gas configurations when I didn't have them arranged that way in the beginning, right? So clearly, hopefully, you can see that that's a different arrangement for the electrons around the atoms that are present. In the end, it's a bit more stable than it was to begin with, so that's why that reaction happens. So I'm describing this to hopefully provide a contrast for you, so you'll recognize the difference between a chemical reaction and a physical change. So maybe you didn't know solvation was a physical change. Maybe you didn't know dissolving was a physical process in your quiz answers. If you didn't know, then what most of you predicted isn't terribly unreasonable. But let's look at what we have in this actual quiz question. What we have here is KBr. So when a K and a Br combine together, what type of bond is that going to be? Ionic. Anytime you have a metal and a nonmetal, it's going to be ionic, right? We wouldn't really need a Lewis structure for this because there's no shared electrons. There's no covalent bonds. And I know that because when a metal and a nonmetal join together, the metal usually needs to lose electrons to make a noble gas configuration, and the nonmetal needs to gain electrons to make a noble gas configuration. So the formula will be such that when the metal loses enough to gain its positive charge and the nonmetal gains electrons and has a negative charge, they will be present in equal amounts, so the charges will be balanced. So I know potassium is only one away from a noble gas configuration. It should have a positive charge. And the bromine has enough valence electrons to give it a negative charge. So you should be able to predict the charges, especially even if only one of those, you could predict the charge based on the number of electrons it needs to gain or lose to make the noble gas, then you could predict the charge on the other one, right? Because they have to have opposite charges and they have to have equal quantities of charge, since the overall formula, it doesn't have a charge overall. So looking at the arrangement of electrons there, is there anything unstable about it? No, there isn't. Both atoms already have a noble gas configuration. In ionic substances, which are also known as salts, and they already have charges, usually they already have charges because those are stable ways to arrange the electrons to complete the noble gas configuration. So I shouldn't be predicting any change in the arrangements of the electrons here. And if I add that to water, same thing, right? We just talked about how water is the most abundant form that hydrogen and oxygen will adopt on our planet, which means it must be a pretty stable arrangement, or hydrogen and oxygen wouldn't stay in that arrangement with those atoms and those electrons that way so often. Plus, we know the oxygen and hydrogens both have complete noble gas configurations. There's no formal charge. There's no instability really there at all. So why would these even come together? So there's no reason to predict a reaction here. So what the question is saying is, I'm going to dissolve KBr in water, and I want to think about what's happening with the solvation. So if you're dissolving it, that just means you're mixing it together, right? If you think about dissolving, hopefully on a macro scale, you might be thinking about a beaker. You have the water as a liquid. You add the salt, the solid, the KBr, and you're seeing the salt disappear, right? The solid is like mixing it with the water, and it's clear. When it dissolves, it's clear. It's not still cloudy. All the solid is mixing in thoroughly. It's a homogeneous mixture. You can't see any separation. So what's actually happening here? True. Yeah, very good. So the H2O is going to surround the salt in order for it to mix. Why would it do that? There must be some type of attraction. We haven't talked about hydrogen bonds yet, and we will, but hydrogen bonds are a type of attraction that don't really involve a rearrangement of the location of the electrons. It's just opposite charges attract, right? We know that. That's really the basis of everything we've been doing in this class. So the K and the Br, we understand why they stick together, right? But why would the water surround them? Why would the water even mix with them? If the K and the Br, I mean, KBr looks kind of like this. I mean, you've got the K and the Br, and they're like alternating back and forth, plus minus, in rows and columns. This is what a solid salt looks like. It has layers of positives and negatives, with all the positives surrounded by negatives, all the negatives surrounded by positives. It's this organized arrangement of charged particles, so all the opposite charges can be next to each other and form lots of attractions. Why would those attractions break up? Because the water is polar, right? Because the water is polar, and because at any given temperature there's motion. So you need motion, the kinetic energy of the individual particles moving around to break attractions, and if you can't reform new attractions that are somewhat equal in strength, then the old attractions would just come back together, right? So some salts are very soluble in water, and other salts are only slightly soluble in water. the difference has to do with the strengths of all these different attractions. Okay, so let's look at the attractions in detail. So in the salt, you have positive and negative charges. Those have to break. So when we're talking about breaking and forming attractions, the ones that break, some of them that have to break are ionic bonds. So this has to, when I put this solid, these chunks of solid in the water and I stir it up, those chunks have to mix in, which means all these charges are separating from one another, and that's ionic bonds breaking. So I've got to break some of those up and get the positives and negatives to separate from one another. Is that a chemical change or a physical change, breaking ionic bonds? It's physical. I'm not changing the arrangement of the electrons. The K plus is still, with the same exact noble gas configuration, it still has the same exact number of valence electrons and arrangement of valence electrons as it had before, and so does the Br minus. This is not a chemical change. Breaking ionic bonds is not a chemical change. Breaking covalent bonds is a chemical change. If I were to break this covalent bond between the oxygen, which almost every one of you did on the quiz, that bond can break, but there's no reason for it to break here, because if I break this hydrogen away from the OH, I create some completely unnecessary charge imbalances, and I also lose a noble gas configuration on the hydrogen. With an H plus, it has no electrons. It can't have the same number as a noble gas. That's really not going to be stable. And if that breaks, which it does actually in water, the number of these particles is going to be very, very small. And most of the time, small enough to ignore, because as soon as they form, what happens to them? They're just going to come back together. So I don't really have to worry about how much of that forms if it's 10 million times less than the amount of water, because as soon as those form, in a matter of seconds, they find one another and come back together again. So if those ions don't really form significantly, there's no significant quantity of them building up in solution, because they just come back together and reform their octets. There's really no chemical change occurring for the water. Why is water a liquid? Why is water a liquid, but oxygen in its elemental form is a gas?
It takes more energy to move the water molecules.
So the difference between a liquid and a gas isn't necessarily that the gas is moving faster, because technically the gas molecules are moving faster if you just think about their speed as like a particle traveling through space, which is called translational motion. But we have to really think about the motion of a particle as including not just it moving through space and translational motion, but also the vibrational motion it has and the rotational motion it has. So if we think about a substance that's a liquid like water, it will remain a liquid pretty much all the way up until its boiling point. So once it reaches its boiling point, which for water is 100 Celsius, at that temperature, then it can become a gas. I mean, there's evaporation that occurs below that temperature, but most of the molecules stay as a liquid, and then at the boiling point, they're converted into a gas, right? So at that temperature, at the boiling point, you could have some of the molecules still in the liquid and some of the molecules in the gas phase. If they're all at the same temperature, they all have ultimately the same amount of average motion or kinetic energy, right? Because temperature is the measure of the average amount of motion or average amount of kinetic energy. So we don't really need water to gain more speed in order for it to evaporate, because we can have water and water vapor or gas, liquid and gas at the same temperature. So we don't have to really change their kinetic energy or their speed to get it to evaporate. What we have to do, the difference between a liquid and a gas, is that in the liquid, the particles are close together. In a gas, they're farther apart. They're separated. So the reason water is a liquid is because water molecules like to get close together. And the reason oxygen at room temperature is a gas is because the oxygen molecules don't get close together so much. Why? What's the difference? Water is polar, right. So, when we talked about drawing Lewis structures and getting the formal charge and the geometry and looking for resonance so that we could predict the polarity of the molecules, here's one example, and we're going to talk about many more, where being able to recognize that a molecule is polar allows us to predict and understand a lot about its properties. So because water is polar, because the oxygen is more electronegative than the hydrogen, it attracts electrons and creates, as the electrons shift toward the oxygen, more negative charge. The electrons are negative, they move toward the oxygen, they bring their negative electron density to the oxygen carries more negative. That pulls electrons away from the hydrogens. And so the hydrogens become more positive. And so one molecule's negative lines up next to the other molecule's positive. What is it called when you have a molecule with opposite charges on opposite ends? A dipole. A polar molecule forms a dipole. What is it called when two polar molecules attract? It's called a dipole-dipole. One molecule's dipole attracts the other molecule's dipole. Can oxygen do that? O2? Not really. O2 has two atoms with equal electronegativities. Why would one oxygen pull the electrons more than the other and create one end that's negative and one end that's positive? It wouldn't. So we don't really have that here. We can't form a dipole-dipole attraction between oxygen molecules, so they don't stick together. That's why oxygen is a gas and water is a liquid at room temperature. That's why water is a good solvent to dissolve salt, because the water molecules are polar. So if you had to think about how are these water molecules going to arrange themselves around these ions, which allows the KBr to dissolve at all, well, the positive ends of the waters are going to get next to the negative ion, and the negative ends of the water are going to get next to the positive ion, right? So that's what this hydration means, or solvation. Hydration is the same as solvation whenever water is the solvent. So solvation is more general, could be for any liquid solvent. Hydration is when water is your solvent. The water molecules will, since the negative end is where the oxygen will come in here and surround. It will face this positive charge and surround it. Three-dimensionally, not just two-dimensionally as I've shown. There will be water molecules coming out of the plane of the board with their oxygen still facing the positive charge. So that forms a partial negative, partial positive attraction. If you had to give that a name, what would you call it? Is it a covalent bond? No, the oxygen's not sharing electrons with the positive charge. The positive doesn't really want those electrons to complete its noble gas configuration, right? It's totally fine with the number of electrons it has. There's no change in the arrangement of the electrons. It just happens that these two particles happen to have opposite charges, and opposite charges attract. So the water molecules simply line up around the positive charge. So the positive charge is an ion, and the water, is the water an ion? No, it doesn't have a formal charge. It's a dipole. It has opposite charges on opposite ends. So that's called an ion dipole. And so the water molecules will also surround the negative ion, but they will face the negative ion from the other end. The hydrogen end will come in here and face the negative charge of the ion. And so I'll have these partial positives on the other end of the water molecules surrounding the negative, again three-dimensionally. So what are the attractions that have to break? Ionic bonds between the positive and negative, Br minus and K plus. And I don't expect you to come up with the term dipole because it's not introduced yet in this chapter, but at least you could say the partial charge attractions between some of the water molecules will also have to break in order to allow the positive charges to come in between the water molecules, right? One water molecule attracts another water molecule through these partial charge attractions. So I have to at least separate those a little bit if I'm going to allow the ions with their full charges to come in there. And what are the attractions that form? Well, so these ion dipoles, the attraction between the full charge of the ion attracting the partial positive and partial negative of water. Is there a limit to how much salt you can dissolve in water? Yeah, if you keep adding salt to water, eventually the solution will become saturated with salt. You can't dissolve anymore. Why is that? Well, now we understand the attractions. Hopefully it should be obvious to you. There's only so much water. I can only surround so many of these ions. If I don't have enough water to surround them, what will happen to the positive and negative charges of the ions? They'll just attract and they'll come back together and I'll reform the solid. And so the amount of water necessary to dissolve this salt, it's going to depend on how strong of an attraction there is between these positives and negatives in the salt. If I had a different salt other than KBr, where maybe I had like calcium 2 plus and like a sulfide 2 minus, and I'm lining these up with the 2 plus 2 minus, is that going to be more or less soluble in water? Probably way less. Because if I have more charge attraction in the salt, it's going to be harder to break that. And once I do break it, if I try to get a 2 plus and a 2 minus separated and keep them separated using these kind of smaller partial charges on the water, it's going to be harder to keep those full charges apart, and they're going to come back together and they're going to reform on the surface of the solid more often.